بس ساكن في ايدي.
Okay, we had this problem on the board last time at the end of class. So let's take a couple minutes to solve the problem. The problem is we have a dam, and we have water in the dam, and it's water in front of the dam, and the dam has a surface of width W and depth D. And the question is, first of all, what is the resultant force from the hydrostatic gauge pressure on the wall? Okay? Now remember, the gauge pressure is the pressure above atmospheric pressure. Okay? So let's take a couple minutes to go through and solve that.
دكتور محمد هو مطلوب ايه بس؟ ما بفهمش انجليزي.
يعني ايه بتفهم انجليزي؟
لا انا بفهم انجليزي بس مش بفهم انجلش. دكتور بجد خلاص كده هو انت الضغط.
So who solved the problem? What was the what?
The definition.
The resultant force?
No, rules. The rules to solve this problem.
Well, this is what we talked about yesterday. It's what we talked about in the last lecture, right? We talked about the dependence of the pressure on the depth.
Yes, but it is perpendicular. It's vertical.
Yes, it's vertical. That's right.
So
Okay. The problem is that the pressure is not constant as you go all along the wall.
عمر هنعمل ايه اهو؟ مرة زي كده طلعت على جنب.
بس مين قال لك انها على الجنب يعني؟
انا كده الدفع.
ماشي بس
The resultant force. Okay, let's go through the problem together. So here's the wall of the dam. Okay? We have a width W, we have a depth D. Let's call this point Y equals 0, and this point Y equals D. So we'll define D, we'll define Y so that it's positive as we go down. So now, the question is, what's the resultant force? So, and the problem is, we can't solve this problem just by saying that there's all the force at one point. Because the force is equal to the pressure times the area, and the pressure is equal to rho times G times the depth, okay? Which in this case is rho G Y, okay? So we can't just identify all of the forces being at a particular point and then just calculate the force. But what we can do is we can cut up the dam into strips of length dy. And all along this strip we have a constant depth. Okay? The depth is y. So here we can say the pressure is constant, and we can say that the force is constant. As long as we take the limit, and this is strictly true, I mean it's approximation the way I've drawn it, but it is rigorously true in the limit where dy goes to 0, where the thickness of the strips goes to 0, and where the number of strips goes to infinity, which is the same as taking the integral. So, what I can do is I can take this part, and I can calculate dF, the force along that strip. And that is going to be equal to the pressure times dA. Okay? And the pressure is going to be rho G Y, and dA is going to be equal to D times dy. So the resultant force will be equal to the integral sorry, yes, W here. W times dy. Okay, so this is the force on one of these strips. So if I add it up all along the dam, then this is going to be equal to the integral from y equals 0 to y equals d. And this then will be equal to, this is integral of df. So I'm going to have rho g w times y dy, and all of this part is constant, so I can remove it from the integral. So I get rho g w, integral from y equals 0 to y equals d of y dy. And this will be equal to rho g w y squared over 2, going from 0 to d. And so this is equal to rho g w d squared over 2. Okay? Yes?
But doctor, this force is tangential to the side, and the pressure is the perpendicular force.
It is not tangential to the side. This is, here's your dam, and here's your fluid, and the pressure is acting perpendicular to the wall.
But isn't that the weight of this amount of water?
It is coming from the pressure from this strip of water. And the amount of pressure coming from this strip of water is determined by the weight of the atmosphere plus the water above it, which is rho gy. But it is going to be exerted in every direction. We said that. Remember in this picture, we had a picture earlier. If I want to measure the force this direction or the force in that direction, they're the same. Because the fluid is pressing on me from all directions. Okay? Yep. Yes. The weight. Oh, the width of the dam. In this case, in this problem, I've given you the width of the dam, and the width of the dam is constant. Okay?
No, the thickness will be, the thickness increases in the dam.
But the thickness, well, the thickness is dy, and we've taken the limit in which the thickness is going to 0. Okay? Yep.
Can I calculate it from the average?
In this case, you can. As it turns out, why? Because the pressure varies in a constant way with respect to d.
Yes.
What we're going to see, though, is in the next part, when you calculate the torque, you can't do that. So another question? Yes. I'm sorry, I can't hear you. So the pressure as we go to the bottom increases, that's right. So why do we do what?
We consider it constant.
Consider it
Okay, so the pressure is not constant. The pressure is equal to rho gy. Okay? Now for this strip, the pressure is constant. As I go this way, it varies. But as I go this way, it's constant. Do you agree? This is the reason we set up the integral. df is for this strip only. Okay? And that's why we need integration. Because then df we can calculate from here because the pressure is constant over this strip. But then we add the contributions from all the other strips. And that's the integration. Okay? Yes?
I can understand why df equals rho gy w ay.
This part is the pressure. This part is dA. dA is W times dy. Okay? All right? And if dy is small enough, then the pressure is constant. Okay? All right, so now the next part is the torque. Okay? So how are we going to calculate the torque? Let's say I want to get the torque again on my strip here. So the torque will be equal to the integral over d tau. Now what's d tau? D tau should be equal to R cross BF. But this is just equal in magnitude to the lever arm, R sine theta. So let's say this is, so we're looking for the torque about this point O. So if this is our point O, and here's R, the lever arm is going to be this part here. Okay, do we agree? This part is R times sine of theta. Okay? So, d tau is equal to d minus y times df. Everyone agree? This distance is d minus y. This distance is d, this distance is y, so the distance here is d minus y. Okay?
عشان الزيرو من فوق.
Okay, so the total torque we get by integrating this. This will be equal to the integral from y equals 0 to y equals d of d minus y times df. And what is df? Rho g y w times dy. So let's remove all the constant parts. I have rho g w, and then I'm going to have the integral. I'm going to have d times y times dy. And then I'm going to have minus y times dy. So this is equal to rho g w. This first term gives us dy squared over 2. Second term gives us y cubed over 3. All of this going from y equals 0 to y equals d. Okay, so we have, this one is rho g w times d cubed over 2 minus d cubed over 3, which is rho g w d cubed over 6. Okay?
Why we use here d minus y and not y only like the first part?
Because in the first one we were substituting for the pressure, and the pressure is rho times g times the depth,
Yes.
which is y. But in the second part we are using the lever arm for the torque. So in the first part we were using, the pressure depends on this depth, and in the second part the lever arm is that distance.
What is the axis of rotation?
The axis of rotation is here. Oh. Okay. So the builder of the dam needs to take into account not only the possibility that the force will collapse the dam, but that it might flip the dam over. Yeah.
Can I integrate the force with respect to the lever arm?
With respect to the lever arm. So what do you mean by that?
I mean the integration of F for dy.
Well, in effect, you see, this is what we've done. We've integrated,
We have
but we
integrated
substituted for the lever arm in terms of y, because otherwise, you see, we have the pressure in terms of y. So if I want to change to another variable, like let's say r or theta, like I could integrate with respect to theta, but then I have to write y in terms of theta, and I have to write the lever arm in terms of theta. So this is a simpler way of doing it.
Okay, but the two ways are the same.
Yes, you can do it. You can write the depth, and you can write the lever arm in terms of the angle theta, and integrate over theta. You can do
That's
that.
the third way.
There's probably other ways you can do it too. Yes?
Can't I use the resultant force?
Okay, that's an excellent question, and it brings us to the final part, the lever arm of the resultant hydrostatic force. So if you use the resultant force, where do you apply the resultant force? Sorry? Because the torque depends on the point where you apply the force, right? Okay, so the last part of the question asks what is the lever arm of the resultant force. So this rho g, we said now is equal to rho w g times g cubed over 6. Notice that this is equal to d over 3 times the resultant force. So what is the lever arm of the resultant force? It's d over 3, right? So, so the torque exerted on this dam is equivalent to the torque that would be exerted by a force sitting here at a point d over 3 from the bottom, with the same resultant force as what we got in part A. Okay? We calculated the resultant force. We calculated the resultant force here. Yeah? How did we, okay, so the reason I say that the resultant torque is equivalent to having the resultant force imposed here is because of the torque. The torque is the lever arm times the force. Okay? So if I had this force exerted at a point d over 3 from this perpendicular distance, then it would give me the same torque. That's what I mean. Okay? Okay, so let's move on now. In terms of our study of hydrostatics, the next principle that we're going to look at is Pascal's law. So Pascal's law says that the pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the containing fluid. Okay? So that all makes sense in terms of what we've learned about incompressible static fluids, right? And we said the pressure is the same if we're going in different directions. Okay? So now, notice this is quite different from when we had the tensile stress. Remember when we had the tensile stress, we said that we have the beam at the bottom, and the force that's on the beam is determined by the weight of whatever you have on top of it. So we can decrease the pressure and decrease the stress by spreading it over a larger weight. But if we have a fluid, that won't work, right? If we spread out the area, then we just have the pressure now imposed on a larger area. So we actually have a larger force. But we can take advantage of that in an instrument like a hydraulic lift. So because the pressure is the same on this area as it is on this area, if the area here is small, the force will be small, and if the area here is big, the force will be big. Okay? So your text also presents to you some instruments for measuring pressure. And all of these instruments use the same principle that we learned about the fact that the pressure is dependent only on the depth. Okay? So in this instrument, we're measuring the pressure within some kind of chamber. Okay? And we attach one end of a tube to whatever it is we want to measure, and the other part is open to the atmosphere. Now we know that the pressure down here has to be constant because it's at the same depth. Okay? On the other hand, the pressure here has to be equal to the atmospheric pressure plus the weight of the fluid that's above it. Okay? And the pressure here at this point, which is equal to the pressure at that point, must be equal to the pressure up here at the top of the liquid plus the weight of the liquid above. Okay? So we can say that the pressure down here, P, this pressure plus rho Gy1 is equal to atmospheric pressure plus rho Gy2. Okay? And then by looking at the difference between the two heights of the two columns, we can get the pressure in the chamber. Now this is a Mercury barometer. Uses the same principle, but instead this is something that we use to measure the pressure of the atmosphere. In order for this to work, we need to get the pressure up here at the top of this chamber very close to zero. So we have a vacuum. Then we can say that the absolute pressure down here is equal to rho times G, where rho is the density of the fluid in here, which might be mercury, so quite a heavy fluid, and then times the height of the column. And that has to be equal to the atmospheric pressure out here. So this is a way of measuring atmospheric pressure.